Investigating viscous force. So to introduce, our question is, what is the value of viscous force on a 0.00836 kilogram metal ball bearing when dropped in corn syrup, dish soap, and water when the ball is at terminal velocity? And what are the coefficients of viscosity of those liquids?
So in order to obtain the viscous force, we need to find the terminal velocity and calculate the drag force of the terminal velocity to subtract from the gravitational force to obtain the viscous force. So in order to do this, we use tracker and Excel to obtain the position versus time, velocity versus time, and acceleration versus velocity graphs to get the terminal velocity. Using this value, along with assuming that the coefficient of drag is 1, we obtain the drag force and subtract it from the gravitational force to obtain our viscous force, and from there, we were able to calculate our coefficients of viscosity. And so for our results, our values for coefficient for viscous forces were 0.0820 newtons, 0.0820 newtons, and 0.05059 newtons for corn syrup, dish soap, and water respectively. And for our coefficients of viscosity, our values were 84.26 pascals per pascal seconds, 11.61 pascal seconds, and 0.60 pascal seconds for corn syrup, dish soap, and water respectively.
So we hypothesized that corn syrup will have the greatest viscous force and coefficient of viscosity, followed by dish soap and then water, because viscosity is a measure of resistance to flow, and that is the order of the rate of flow for each fluid, from least to greatest.
So when an object falls to a fluid, there are always three forces acting on it: the viscous force, the inertial drag force, and the gravitational force. The viscous force occurs because the fluid resists motion due to friction between layers of the fluid, and the object falling into the fluid will often drag a layer of the fluid along with it, causing this viscous force to oppose the motion of the object. And the drag force is caused because the object exerts a force onto the fluid as it falls to the fluid, and the fluid exerts an equal and opposite force back onto the object due to Newton's third law. And of course, gravity is just negative mg and it's constant. And the net force using the system on the ball by Newton's second law is represented in the equation shown on the bottom right hand corner.
And so this is our system schema for all three experiments. The metal ball, bearing, earth, and liquid are all within the system, and their interactions are shown here. And this is our force diagram approximately for all three experiments. The force of viscosity and force of inertial drag will differ depending on the type of fluid the metal ball bearing is dropped. And then at terminal velocity, the force of gravity will equal the force of viscosity plus force of inertial drag. And these are our energy diagrams. So before the ball is dropped, it has all potential energy within the pie chart, but as it travels, potential energy will decrease, internal energy will increase, and at terminal velocity, the kinetic energy will reach its maximum. So the calculation of density is seen here. The reason why we calculate density is to input it into the formula for force of inertial drag, and our density values for each fluid are shown right here.
When analyzing a corn syrup data, the acceleration of the position versus time graphs and the velocity versus time graphs are very small and hard to see, but they are still there, indicating that the terminal velocity is not too different from the initial velocity. And we obtained our terminal velocity using the x-intercept of the curve fit of the acceleration versus velocity graph based on our model, and we obtained a value of negative 0.00826 meters per second.
And so these right here are our calculations. We use the formulas to the right for force of inertial drag and force of viscosity. And so we found that the force of drag is approximately 0 newtons. The value was insignificant, and the force of viscosity was 0.082 newtons, and the coefficient of viscosity is 84.26 kilograms over meters second.
Looking at the dish soap data, it's clearer to see that there is an acceleration here, because there's a clear curve to the position versus time graph, and there is a clear upward trend in the velocity versus time graph. Again, we used the acceleration versus velocity graph and found velocity when acceleration equals 0 to obtain our terminal velocity, which was negative 0.599 meters per second.
And we did the same calculations here, finding that the force of drag is approximately 0 newtons, the force of viscosity is 0.082 newtons again, and the coefficient of viscosity is 11.61 kilograms over meter second.
Looking at the data for water, again, here it's even clearer that there's an acceleration looking at both the velocity versus time graphs and the position versus time graphs. However, looking at our acceleration versus velocity graph, we simply do not have enough data points to calculate a reliable terminal velocity. Instead, we use the observation that for the last five frames, the position versus time graph and the velocity versus time graphs were roughly linear, and we obtained our terminal velocity by using the y-intercept of the velocity versus time graph, which was negative 0.7156 seconds.
And lastly, our calculations here for force of drag is 0.03142 newtons, force of viscosity 0.05059 newtons, and coefficient of viscosity 0.6 kilograms over meter second.
In conclusion, corn syrup and dish soap had roughly the same viscous forces, which were both greater than that of water, as you can see in the list of viscous forces above. And corn syrup had the greatest viscous coefficient value, with dish soap following and water with the lowest. Some potential errors were that resolutions and pixels of camera were simply not high enough to accommodate how slow the ball fell through the corn syrup. And another error is assuming that the coefficient of drag is 1, which could really affect our water data because as you can tell from our calculations, the water would be the water had a significant drag force. A third source of error is not clicking on the same spot of the ball bearing each time. And finally, corn syrup and dish soap accelerations versus velocity graphs had a lot of positive accelerations, indicating that there might have been a terminal velocity, that might have been initial velocity before dropping them into the liquids.